In this video, we're going to think about why we have seasons on Earth, like summer and fall and winter and spring. Now, one theory that some folks might have is maybe it's due to the distance between Earth and the Sun. We know that the Earth orbits the Sun. The Sun is where the great majority of the heat and energy on the surface of the Earth comes from. And maybe it's the case that when there's certain times of the year when we are further from the Sun, and there's other times of the year when we're closer to the Sun. Well, this does not actually hold up to why we have seasons. Because, first of all, when the northern hemisphere, the top half of the Earth has winter. The bottom hemisphere has summer and vice versa. So it can't just be due to the distance of the whole planet. It also turns out that when Earth is furthest from the Sun is in July, which is in the middle of summer and the northern hemisphere, and when we're closest to the Sun is in actually January, which we know tends to be our colder season in the northern hemisphere. So distance to the Sun does not hold up to why we have seasons. The real reason why we have seasons is because Earth's axial tilt. I guess you could say that it's a rotational tilt. Now this picture shows that the tilt. But before we go into it, I'd like to remind folks that this is nowhere near at a drawn scale. The actual Sun has a diameter over 100 times out of Earth. 1 million Earths can fit in the Sun, and the actual distance between Earth and the Sun is over 100 times the diameter between this Earth and the Sun. But going back to the tilt, and you can see that here in this picture, Earth's North Pole does not point straight up from the plane of Earth's orbit around the Sun. What do I mean by the plane of Earth's orbit around the Sun? This red circle that you see, or this ellipse that you see, if you imagine that being on the surface of a table or a plane, that will be our orbital plane. And we can see that the North Pole does not go straight up from that, and the South Pole does not go straight down. And actually, we're looking at an angle of about 23.5 degrees. And that's the reason why we have the seasons. To imagine why that is the case, let's imagine Earth when the northern hemisphere is most pointed towards the Sun, which happens in the late June. So let me draw the equator to help us visualize this a little bit, and let us compare that to where the northern hemisphere is most pointed away from the Sun, which happens in late December. So we'll draw the equator again to help us visualize this. Well, let's pick a similar point in the northern hemisphere. So let's pick a point that is a little bit above the equator. So let's say that a point and a comparable point in this scenario is going to be right over here. Is that the same distance above the equator? Notice, in late June and the northern hemisphere, the Sun is almost directly above the white point that we are seeing here. And while in this scenario, the Sun is at an angle. The surface of the Earth is more like this. So the Sun's rays are coming at an angle. And if you think about it, think about the scenario. The difference between the Sun is directly bearing down on something versus when it's coming at an angle. Let's say this is a side view of two surfaces. And the surface on the right has twice the surface area. You can see that the side view has twice the length. So the surface area, if you were to see it in 3D, would be twice the surface area of what we have on the left here. But if you have the same amount of the Sun coming from the same direction, so here, let me draw these 3 sun rays here. This is just an indirect, and let me draw 3 sun rays here. Notice you have the same amount of energy, but there you are hitting twice the surface area. So amount of energy per unit surface area is going to be half as much in the scenario where the Sun is coming at an angle versus this scenario where the sunlight is coming more directly on top of that point. And wherever you go in the northern hemisphere, the angle is less direct in the winter than it is in the summer. Now there's also some effects on the amount of daylight you get. For example, in the summer, when the northern hemisphere is most tilted up towards the Sun, in the North Pole you're going to have constant daylight, and the South Pole you're going to have constant nightmare. And then the opposite happens when the northern hemisphere is pointed away. And then we can think about spring and autumn in either hemisphere. You can see that the angle of Earth's rotation does not change from that 23.5 degrees, but in spring and autumn the northern hemisphere is not pointing to or away from the Sun. It's kind of just point to the side. So in these 2 points, comparable points on the northern or southern hemisphere are seeing similar angles of actual sunlight. Sorry.